Hello, everyone. Welcome to my talk on the stop-start control of seismicity at fault bends along the Main Himalayan Thrust. I will be talking about how we use physics-based numerical modeling to understand the role of structural complexity in the seismic cycle of the Nepal Himalaya and better constrain Main Himalayan Thrust fault geometry. On 25th April 2015, an earthquake with moment magnitude 7.8 unzipped the lower edge of the MHT in central Nepal. It ruptured a 50-kilometer wide segment, creating great havoc to life and property. The seismic cycle at MHT exhibits both along strike and down dip segmentation. From paleoseismic studies and historical data, we know that this fault system likely slips in large surface rupturing giant earthquakes with recurrence intervals in the order of 500,000 years at various locations across the Himalaya, like the 1934 Nepal Bihar earthquake and the 1505 earthquake. But there are also blind ruptures that break only the deeper sections of the fault, like the 1833 Kathmandu event and the most recent 2015 earthquake. It is important to understand what determines the spatial extent of seismic ruptures to produce realistic bounds and seismic hazards. Interestingly, this is an area that hasn't had a complete rupture in the last 500 years. And as you can see, this area is in between historical earthquakes to the east and west. This seismic gap has accumulated almost 10-meter slip deficit along most of the stretch of this front. But it turned out that the Gorkha only ruptured incompletely, and it isn't the great earthquake that was anticipated for this region. In this paper, we try to answer these scientific questions of interest. What controls earthquake segmentation? Why did the Gorkha earthquake terminate in the middle of the seismogenic zone? What is the role of fault bends in the seismic cycle? And what are the future seismic hazards in the Kathmandu and the Himalayan region? Fault geometry of the MHT and the presence of ramps is highly controversial. But we know that the MHT geometry is not planar. And the most important piece of evidence comes from surface geology and the existence of the Gorkha Pokhara anticlinorium. You need this mid-crustal ramp to create this large-scale and long-term structure. And thanks to the Gorkha earthquake, we know that the MHT is flat, or the portion that ruptured during the earthquake was sub-horizontal. But there are also other geometric features in this highly corrugated fault system, which remain debatable. So we're going to look into two n-member models of non-planar MHT fault geometry that reconcile several different datasets. The first n-member model is from the study published by Elliott and others, uses the coseismic geodetic data based on what is known about the fault geometry at depth from geology. The fault structure consists of three segments. It's a ramp-flat ramp geometry, a shallow 30-degree north-dipping ramp between the surface and 5 kilometers depth, constrained by structural sections in the area, and following the surface trace of the main frontal thrust, MFT. Second, a flat portion with a shallow angle, reaching finally a steeper mid-crustal ramp. Both the coseismic data and electrical conductivity studies show a flat décollement with a shallow angle. And seismic reflection profile shows the location of the main reflector coinciding with the deep décollement. Hence, it makes sense that a mid-crustal ramp connects the flat décollement under the lesser Himalayas and the deep décollement under the higher Himalayas, which also explains the existence of the Gorkha Pokhara anticlinorium. The second n-member fault geometry model, Model H, was published by Hubbard and her group, and is a geologically informed model of the MHT that is also consistent with seismic observations from the Gorkha earthquake. This study builds a comprehensive structural cross-section based on the kinematic fault bend fold model, and it also incorporates surface geology. This model includes a ramp in the middle of the seismogenic zone, and this numerical simulations of the seismic cycle in Nepal based on these two n-member fault geometry models. We use physics-based rate and state-dependent friction law with the boundary integral method. We employ the multiplicative form of the rate and state friction, where the fault strength depends on the area of contacts that bear the normal and shear loads. We use uniform frictional properties because the spatial variations of frictional properties in the MHT are poorly constrained. And so we consider simple cases of homogeneous frictional properties in the seismogenic zone and the aseismic region underneath. So the fault is velocity weakening all the way from the surface to 15-kilometer depth for both geometry models. Velocity weakening regions are where earthquakes nucleate and have decreased frictional resistance following a velocity jump. At greater depths, the higher temperature favors the transition from frictionally unstable velocity weakening behavior to stable velocity strengthening. There is increased frictional resistance following velocity jump. Now, this depth range also coincides with the microseismicity, and we believe the mid-crustal ramp operates as the asperity during interseismic periods where elastic strain builds up and accounts for much of the convergence rate. The spatial distribution of the frictional parameters control many aspects of the fault behavior. Different physical parameters control various different aspects of the seismic cycle. So we use non-dimensional numbers to identify the combination of parameters that control rupture dynamics and rupture style. The first non-dimensional parameter that we explore is called RU here, represents a ratio of the seismogenic zone size, which is the size of the velocity weakening region, to a characteristic rupture nucleation dimension. You get stable fault slip in the velocity weakening regions with low values of RU because of the large nucleation size compared to the fault dimension. Higher values of RU gives rise to chaotic cycles with full ruptures followed by partial ruptures. Here, I'm showing you how the dynamics change as the value of non-dimensional parameter RU increases. The panel on the left corresponds to fault geometry model H, while the panels on the right correspond to fault geometry model E. The x-axis depicts time steps that are not uniformly spaced, so it's not time itself, with fast events having a finer resolution than during the interseismic periods. The y-axis is the down dip distance. Color indicates the fault slip rate. Red reflects seismic velocities and black denotes fault locking. We show that self-emergent partial ruptures are for RU values greater than 20 with model E and 6 for RU greater than 6 for model H. The presence of a middle ramp is the reason why partial ruptures emerge for lower values of RU because the middle ramp affects the overall shear stress on the fault. The second non-dimensional parameter that we explore is RB, which is the ratio of the static and dynamic stress drops. A and B are rate and state frictional parameters. A quantifies the direct effect of a slip rate change. Parameter B describes the effect of the state variable. This ratio controls the style of rupture and the relative fraction of the rupture energy consumed in fracture. Large RB values favors strong weakening behavior with proportionally limited fracture energy. And as you can see, many of these models are able to capture several aspects of the MHT seismic cycle. They produce cycles of full and partial ruptures and aftershocks at both fault bends and as well as in the transition zone between velocity weakening and velocity strengthening regions. Among all these simulations, we retain those that best explain surface slip observations and inferred slip distributions of the Gorkha earthquake. In particular, we have geodetic data from the GNSS network and INSAR data from HALO satellites. I'd like to point out that we are operating in a two-dimensional world, mainly for computational reasons. So we use fault geometry models along a representative cross-section AA dash that is perpendicular to the plate boundary and crosses the Gorkha-Pokhara anticlinorium in the middle of the Gorkha coseismic rupture. Here I plot surface displacements from my models with the two fault geometries and compare against the INSAR and GNSS data. The top two panels here show two INSAR scenes from the HALO satellite, which clearly observe the subsidence of the high Himalayas and uplift in the Kathmandu region. The red line here is the line of sight INSAR displacements from these two scenes. And the black dashed and solid lines are from my models, and it agrees quite well. Here we compare surface displacements from GNSS data The red points are from the far field stations which did not observe much of the surface displacement. The fault slip was buried and these stations were not close enough to capture it. But the blue data points are from the near field GPS stations. Again, there is general agreement with our models, especially vertical displacements. The discrepancy with geodetic data are mainly because the models are missing all the along strike variations, since ours is a 2D model. The bottom right panel here shows a comparison between our models and the inferred slip distributions obtained using the two geometries. We're now going to look closely at the details of our preferred seismic cycle with fault geometry model E. Here you see seismogenic zone is fully locked during the interseismic period. There is some creep associated with the shallow fault bend, but I don't think it can be detected by geodesy. All the ruptures, both partial and complete, initiate close to the transition zone between velocity weakening and velocity strengthening region, which is also close to the mid-crustal ramp. And this region is a region of very high interseismic stress buildup. Here I plot the shear stress accumulation on the fault against the down dip distance for a period of 5,000 years. Red indicates regions of high stress accumulation, and light blue to dark blue are areas of low stress. You see how the down dip edge of the transition zone is loaded and has high stress accumulation throughout the cycle. In addition, previous ruptures also leave behind notable stress residuals that explains the subsequent down dip rupture segmentation due to non-uniform pre-stress along the fault. No aftershocks updip of the Gorkha earthquake, but there are down dip aftershocks following large ruptures where afterslip rapidly decays in the days, months following the earthquake. This figure here shows the time history of the megathrust behavior using the fault geometry model E. And this plot highlights the spatiotemporal evolution of slip. The red lines are complete ruptures that break the entire seismogenic width, and the purple are partial ruptures. I've highlighted the Gorkha-like events in blue because it closely matches the Gorkha earthquake data like we saw earlier. We define a super cycle as a period that separates two consecutive through-going ruptures and encompasses one or several partial ruptures. So the super cycles here are fairly periodic with partial ruptures that have similar size and extent. The recurrence time between complete ruptures range between 1,300 to 1,700 years. Next, we look into the details of the seismic cycle using fault geometry H. This is a model that includes the middle ramp in the seismogenic zone. The presence of the middle ramp affects several interconnected aspects of the seismic cycle. First thing is the middle ramp is able to act as a geometric barrier, stopping ruptures as in the case of Gorkha earthquake. But it also allows ruptures to pass through it, creating larger partial ruptures. And there are also ramp spanning ruptures that break this region in smaller partial ruptures. As expected, there is a lot more activity going on with this model. So we can see high stress concentrations, not only from the down dip edges and previous earthquakes. Fault bends attract persistent seismicity at the middle ramp. So whether or not ruptures pass the ramp depends not just on the fault bend, because if that was the case, all ruptures would be stopped at the fault bend. It also depends on the history of previous seismicity and the spatial distribution of pre-stress. So some ruptures, like the Gorkha-like events, like event 43 and 65 here, are stopped before they reach the middle ramp, while other ruptures like event 50 and 57 extend beyond the ramp. So if you look at the spatiotemporal evolution of slip, there is almost thrice the variability seen in model H compared to model E in recurrence times, because the through-going ruptures repeat anywhere between 900 and 2,000 years. Supercycles are more aperiodic or chaotic, containing partial ruptures of varying sizes. Another important difference is that the variability in hypocenter locations denoted by stars here. Ruptures don't necessarily all start from the down dip region, but have multiple initiation points. Most of them are associated with fault bends, where we saw were areas of high stress concentrations. The most exciting point about the model with the middle ramp is that it is also able to reproduce up-dip aftershocks. In the 12 hours following the main shock, there were 7 immediate aftershocks relocated using advanced waveform techniques. These 3 highlighted here occurred up-dip of the main shocks, roughly around the same location as the middle ramp. In our model with the middle ramp, an up-dip aftershock occurs about 14 hours after the main shock. I have plotted here 3 observation points, A, B, and C on the middle ramp, and 2 on the flat portion where the main shock happened, D and E. And I plot here the peak slip velocity at these observation points during and immediately after the earthquake. Triggering of earthquakes or triggering of aftershocks at the boundary of the coseismic rupture can be caused by rapid stress changes, but this type of event does not occur with fault geometry E. These up-dip aftershocks are likely associated with geometric features like the fault bend. Fault bends are prime regions of aftershock triggering because the stress level is already elevated at the start of the main shock. Obviously, we are not able to reproduce the rich scenario of aftershocks both at the up-dip and down-dip edges of the earthquake. Again, this is because we have computational limitations as well as limitations due to two-dimensional geometry. Finally, the difference in complexity of the rupture sequence between these two models can also be illustrated using distribution of rupture sizes. In nature, seismic sequences follow power law statistical distribution like the Gutenberg-Richter. Here, I'm plotting the cumulative histogram of all the events in the catalog for both geometries. The yellow corresponds to the fault geometry with the middle ramp and follows a power law distribution with rupture sizes spanning 4 orders of magnitude. In conclusion, I'd like to circle back to the questions we asked ourselves earlier and summarize on what we have learned so far. What controls earthquake segmentation? The impact of fault geometry is multifaceted and cannot be deconvolved from the frictional control. Fault bends impose a complex footprint on the megathrust seismic cycle. What is the role of fault bends in the seismic cycle? A middle ramp in the seismogenic zone is essential to consistently explain both the coseismic as well as the early up-dip aftershocks. The complexity of stress interactions due to morphological gradients translates to a wider range of rupture sizes and extent. In order to evaluate future seismic hazards, some of the possible scenarios are repeat of the 2015 event, or break the up-dip lock portion, or break the entire MHT in a single rupture. Here I'm plotting the slip accumulated against the down-dip distance. The color is the fault slip rate. The black contours are cumulative coseismic slip values plotted every 5 seconds, while white contours are cumulative aseismic creep plotted every 50 years. You can see that in both models, the large slip deficit in the shallow regions of the fault are recovered during complete ruptures. This could be mainly because of the fact that when you have brought all the stress to the front, the entire fault is ready to break all in one go. So the chances of a partial rupture of just the up-dip lock portion seems unlikely based on the assumptions of this model. Before I conclude the talk, I'd like to highlight some of the missing pieces from this giant puzzle, like how does off-fault deformation and folding processes affect the long-term and short-term deformation of the Himalayas? What are the other geometric and frictional heterogeneity in the along strike direction? And what are the effects of topography on the seismic cycle? Thank you for watching this video.